On Friday, September 28, 2018, on the island of Sulawesi, Indonesia, an earthquake followed by a devastating tsunami destroyed the Bay of Palu. Within minutes, 4,000 people lost their lives and 79,000 others had to be evacuated. How could such a tragedy happen again after the 2004 tsunami that already devastated Indonesia? Two tsunami specialists, Professor Kostas Sinolakis of the University of Southern California and Professor Herman Fritz of the Georgia Institute of Technology, were sent by UNESCO and the Indonesian authorities to investigate the causes of the tragedy.
Quite impressive to see the devastation. We're now 3 weeks after the event. And here we can kind of see why it's important to come up as quickly as possible, or at least once the emergency is over, because a lot of bulldozing in this area already, so a lot of evidence is already lost.
For those who know how to look, these fields of ruins hold clues of the wave passage. But time is running out. The monsoon will soon wash away the remaining traces.
Working as a tsunami scientist is very much like being a detective on a crime scene. There is multiple murders that have taken place. You really have to piece, like in a puzzle, the sequence of events. Did the tsunami hit first and this made the houses collapse, or were they collapsed because of the earthquake and the tsunami finished them off? What were the people doing? Why is it that some people died and some people did not?
Both investigators want to understand how the disaster unfolded. Their goal, to trace the tsunami back to the original event that triggered the wave. In the small fishing town of Wani, Kostas Sinolakis goes to meet the survivors. Abdulatif miraculously survived. When the wave came, he was on his boat 100 meters from the shore.
Hey! Sir, get off the boat! Get off the boat! At the time of the first wave, when there was the big tremor, I went out on the deck of the boat.
Did you feel the tremors on the boat?
Yes, the boat shook because the water had gone down and the boat was grounded.
What did he do at the time? He stayed with the boat?
Did you stay on the boat?
In front, over there, I was holding onto the mast.
Oh, okay.
And then I saw the wave breaking in the distance. It was very fast, in no time at all, it was next to the boat, pushing us.
About how high was it?
I had time to see my house. The top of it was almost at the same height as the boat.
Where is your house?
Over there. The wave was about 5 to 6 meters high, the height of my house.
For Kostas Sinolakis, this tsunami is an enigma. How is it possible for a 5-meter-high wave to crash through here when a bay is usually protected from tsunamis? "20 kilometers south of Wani, Herman Fritz is investigating in the town of Palu, where thousands of people lost their lives. With the help of 2 Indonesian scientists, Herman Fritz goes to the parking lot of the shopping center overlooking the bay. In order to understand the dynamics of the wave, he relies on another kind of witness: mobile phone videos.
This is the exact spot that we saw on the video. Here you can see the billboard.
Yes. Tsunami wave coming, people running away.
People running away. Yeah, oh.
And that's the second wave.
That's the second
wave. Okay, that's the highest one. So now we can basically see how high the water is, almost from the top of the billboard.
Here, the wave reached over 4 meters in height.
Yeah, so 1.6 here. Okay, 4 up there. Okay.
Ini ya Allah, tsunami ya Allah. Ya Allah, tsunami ya Allah.
To trace the source of the tsunami, Hermann Fritz needs to establish a model of the devastating wave, determine its height at different points in the city, and measure how far it spread inland.
I'm going to try to do some detailed surveying here, so we're going to try to get a full 3D scan. And the purpose of that is to get a 3D space. Basically, the LiDAR scans all the point cloud, and we can see how the waves go through it. So can we measure how high the wave is at every given instance, and how fast the wave is moving across through the houses, washing away the houses, and across the street.
Hermann Fritz tracks the wave. After submerging the parking lot, the water penetrated deep into the city. In this mosque, which is only 100 meters from the shore, clues bear witness to its power.
This one's broken. We have this grill here, and we see this rafted debris inside. So we know that the tsunami was at least to this height of this rack. And then up here, we see the actual primary tsunami line, which is this one right here. And we can also see it in the window. If you look at the blue sky, we actually see a mud line going through there. And then we look at it over here, we also see the mud line coming around, coming around, coming around. So the tsunami is coming pretty much at the height of my head through this mosque. And that's also a very difficult height already, because usually when the water is to this height, you cannot stand anymore. You will be thrown to the ground by the water, so it can be difficult to survive.
After 3 days of fieldwork, the two American researchers and their Indonesian colleagues are finally able to produce a first simulation of the tsunami that submerged the Bay of Palu. According to their observations, the most powerful waves spread more than 300 meters inland. But for Kostas Tsunalakis and Hermann Fritz, the investigation has only just begun. They now have to identify the event that triggered this murderous wave and determine how it could have swept into the bay. Tsu, the port; Nami, the waves. The waves that destroy the port. This word, now universal, dates from the 17th century. It comes from the other place on the planet most frequently affected by tsunamis: Japan. It was coined by fishermen who returned on a storm-free day to discover their port completely devastated by the waves. The most recent tsunami in Japan in 2011 caused the nuclear accident in Fukushima. Following a 9.1 magnitude earthquake, the devastating wave killed more than 18,000 people.
A tsunami has no meteorological cause. The primary cause of tsunamis are earthquakes and earthquakes at sea.
The vast majority of tsunamis are generated by the planet's tectonic activity. The Earth's crust is broken up into several large plates. Magma pushes them against one another a few millimeters to a few centimeters a year. The oceanic plates slide beneath the continental plates, forming subduction zones. Friction between the plates causes deformation of the continental plate, which accumulates a gigantic amount of energy. When the tension is released, it generates a huge undersea earthquake.
The earthquake displaces all the water at once. So if we are 4 kilometers deep, we have 4,000 meters of water that moves at the speed of an airliner. Very quickly, as we approach the coast, the speed is reduced, the wave gets bigger, and we find ourselves on the coast with waves of 20 to 30 meters, as we saw in 2011.
You cannot separate earthquake science and tsunami science. The longer the duration of the earthquake gives a very good indication of how strong the earthquake is. It's like a zipper. If you have a small earthquake, it's a short rupture area. And that means the duration is shorter. If it's a big earthquake like Sumatra, magnitude 9, or Japan, magnitude 9 plus events, then basically you have a very long zipper. That means the shaking will go on for several minutes.
Jesus Christ, look at that. Fucking hell. That wave is a good 15, 20 feet tall. Easy.
The longer and more intense the undersea earthquake, the more powerful the tsunami it generates. This is what happened during the terrible earthquake of December 26, 2004. In the Indian Ocean, a fault located 100 kilometers off the coast of the town of Banda Aceh on the island of Sumatra, Indonesia, broke on a line of 1,200 kilometers. The earthquake, with an exceptional magnitude of 9.1, lasted more than 5 minutes. 15 minutes later, 35-meter waves hit the coast. Continuing across the entire Indian Ocean, the tsunami claimed a total of 230,000 lives. A huge human disaster captured live for the first time by hundreds of video cameras. This disaster revealed the devastating power of tsunamis to the whole world. Before it, little was known about these deadly waves. For the scientific community, it is a wake-up call. It energized the science of tsunamis, which until then was in its infancy. Numerous international studies are launched. The research of Indonesian geologist Nazli Ismail will lead to a major revelation.
Here the tsunami reached 30 meters high up to the top of the hill over there. People rushed to the mountains, but very few survived.
Surveying the coast for traces of the tsunami, Nazli Ismail made an exceptional discovery 30 kilometers south of Banda Aceh.
After the 2004 tsunami, this cave was full of debris, full of pieces of wood. This cave has a very particular architecture. It is L-shaped and its entrance is parallel to the coast. So every time the water of a tsunami comes to submerge this cave, it is retained inside.
Nazli Ismail had a hunch. If this cave trapped the material carried by the 2004 tsunami, it could also hold the memory of past catastrophes. The cave had another particularity: bats. They have colonized it for millennia.
Each tsunami is covered by a layer of guano. You can see the layers of guano in black here.
Over the years, layers of guano, or bat droppings, deposited between each tsunami have become fossilized. They mark a clear boundary that delineates each event.
A layer of tsunami, then a layer of guano. A layer of tsunami and more guano. Then a tsunami, then more guano. Tsunami, then guano, and the 2004 tsunami.
With the help of researchers from Singapore's Earth Observatory, Nazli Ismail is able to date 12 deposits by carbon-14. They tell the story of tsunamis in this region over the last 10,000 years. The upper deposit corresponds to the 2004 tsunami. The next event is about 2,900 years earlier. Then, 4 tsunamis occurred 25 years apart, about 3,300 years ago. The oldest was about 7,500 years ago.
From the data obtained here, we have discovered that tsunamis are recurring irregularly. This is a lesson for both the government and the people. We have to be vigilant, to be constantly ready, because this disaster can happen at any time.
This exceptional discovery is a game changer. Now scientists know that where a tsunami has once struck, another can strike again. Now the question is, where have tsunamis occurred in the past? Since 2008, UNESCO has kept a worldwide tsunami map, updated with scientists' latest discoveries. Over the past 3 millennia, 1,200 tsunamis have been confirmed. The least destructive are in white, and the most deadly in red. Any one of them might become a potential tsunami in the future. 70% of tsunamis are located along the Pacific Ring of Fire, where subduction zones are concentrated. But they have occurred elsewhere on the planet, particularly in a region thought to be spared of this kind of disaster, the Mediterranean. In Nice, thousands of tourists enjoy the pleasures of the beach. But a stone's throw away, a team of scientists from the GeoAzur laboratory are in search of the cause of a forgotten disaster. Digging through regional archives, researchers discovered that on February 23, 1887, an earthquake followed by a 2-meter-high tsunami hit the coasts of France and Italy. From Nice to Genoa, 600 died and tens of thousands lost their homes. Today, 2 million people live along the Riviera. Can such a disaster happen again? GeoAzur's scientific team is looking for the fault at the source of the 1887 earthquake to assess its condition.
2 Italian scientists, Taramelli and Mercalli, recorded at the time, in a very precise way, all the destruction that happened on the coast. We have 2,700 observation points between France and Italy.
Christophe Larocque and his team used these photographs, taken at the time of the disaster, to establish a map of the earthquake's intensity. The more important the damage, the closer the source. It led them to locate its epicenter off the coast of Imperia. But identifying the exact fault responsible for the tsunami is a delicate task, because this seismic zone is one of the most complex in the world. The African plate, in the south, rises toward the Eurasian plate, in the north, pushing Corsica and Sardinia against the Riviera, generating numerous seismic faults. How can the fault responsible for the 1887 tsunami be identified?
We're using sophisticated seismic investigation equipment, which consists essentially of cannons, which are a source of waves, which will permit us to obtain a sonogram of the inside of the Earth up to 15 kilometers deep. These waves will be recorded by the sensors we have within the line, a line that is 6 kilometers long, dragged behind the boat.
After 5 days at sea, the ultrasound reveals not one, but 3 faults below the seafloor. Their location, 30 kilometers from the coast, corresponds to the epicenter of the 1887 earthquake. The morphology of the faults suggests that they are still active and allows the scientists to model 2 possible tsunami scenarios.
The first scenario is an earthquake equivalent to that of 1887 with a 6.7 magnitude, which would break a fault length of about 30 kilometers with wave heights of 2 meters. The second extreme scenario is to envisage a rupture over almost the entire length of the fault, for example 60 to 80 kilometers, which would then produce an earthquake of magnitude 7 and wave heights that could reach 3 to 4 meters.
The Mediterranean, the world's leading tourist destination, is at risk. But scientists cannot predict when such an event might occur. Since 2012, the region has been monitored 24 hours a day by CENALT, a tsunami warning center. Evacuation plans have been drawn up with a focus on Nice. But the reality remains. The rupture of a fault located 30 kilometers from the coast only allows a 20-minute evacuation time before the wave breaks.
Even a small tsunami can be very devastating. A wave breaking on the beach with a speed of around 40 kilometers per hour will create extremely strong currents in which people cannot swim.
Mediterranean beaches, just like many beaches in the Indian Ocean, are very high risk. The reason is that in the summer, we can have tens of thousands of beach visitors on a beach with the possibility of a tsunami arriving, within a few minutes.
Coastlines are popular with locals and tourists all over the world. This makes tsunami warning systems all the more necessary. In Palu, where Kostas Tsunalakis and Herman Fritz continue their investigation, a tsunami warning system was set up after the tragedy of 2004. So why were there so many victims 15 years later?
There were a lot of food vendors right here, a lot of people. There was a rumble, like this. People were shouting all over the place, "The water is rising! The water is rising!"
According to this witness, the crowd in the streets along the beach was completely surprised by the wave. No alert reached this area. The investigation continues at the Tsunami Monitoring Center in the Indonesian capital, Jakarta. This control tower monitors seismic activity throughout Indonesia, including the Bay of Palu. Here, seismologists can detect any earthquake at sea in real time. Advanced algorithms allow them to simulate the formation of a tsunami and warn people before the first wave hits. Since its implementation in 2008, 22 alerts have been issued and countless lives have been saved. Then why, on September 28, 2018, was no warning received in Palu? That night, seismologist Kian Purnasinki was on duty.
At the time of the earthquake in Palu, the magnitude was 7 for 2 minutes. Then just afterwards, the magnitude rose to 7.7. At that time, I ran to the TOES table. It's the tsunami simulation table.
In the early evening, an earthquake 80 kilometers north of the bay was clearly detected by Jakarta.
The epicenter is here. Palu is there.
According to the simulation, this earthquake presented only a moderate risk of a tsunami. Nevertheless, an alert was triggered within the prescribed time limit, 5 minutes after the earthquake. So what happened? Tsunamis will discover the answer thanks to surveillance cameras. Friday, September 28th at 6:02 p.m., the earthquake hits the Bay of Palu. It lasts a little over a minute.
How did you feel about the earthquake? Was it really incredible? You couldn't stand up?
Impossible. I was there under camera 2. I was hanging onto the gate, and then it calmed down and I came out.
That after the earthquake, because he's so close to the water, perhaps a tsunami will come.
They've always said a bay is a bay. It doesn't have tsunamis. They always occur in the open sea. And yet, it did happen right here.
These images provide researchers with crucial information: time. The clock displayed on the videos reveals that barely 2 minutes elapsed between the end of the earthquake and the onset of the tsunami. Never before was such overpowering speed recorded. The warning signal, launched by the Jakarta control system, was triggered after the arrival of the wave, when all communication systems on Palu were already destroyed.
What is very alarming to me is that here, the earthquake triggered the tsunami very quickly. So we need to understand how this happens, and also what is the timing, how quickly after the earthquake hits, the tsunami comes in.
According to the Jakarta Center simulation, a wave born close to the epicenter, 80 kilometers north of the bay, should have taken about 15 minutes to reach Palu, not 2 minutes. This tsunami defies all known patterns. How could the wave arrive so quickly? To figure it out, the researchers take to the air.
It's extremely important to us to have a bird's eye view of the entire place, because by being up on the air in a helicopter, it allows us to see how this wave came in and see the extent of the inundation.
A first observation is surprising. Devastation alternates with untouched areas. But that's not all.
So once you get outside of the bay, the wave disappears very quickly, and you're looking at very beautiful Indonesian beaches. So that already allows to confine the zone where to look for further for the sources to inside the bay.
If the wave that devastated Palu had formed in the ocean, the entire coast would have been hit. For Herman Fritz and Kostas Sinolakis, the epicenter identified by the Jakarta Warning Center could not have directly generated the killer wave. The source of the tsunami must be inside the bay itself. Herman Fritz and his Indonesian colleague, Guérin Parasetia, returned to the West Bank to understand how the tsunami could have originated in this sheltered area. Guérin Parasetia has collected new footage filmed nearby.
The bar is still over there, the same position.
Yeah.
So then you can see also the background of these events, and then this is when they started the landslide.
Yeah, local landslide, co-seismic triggered by the earthquake. You have a small semicircular wave that you can even see in the video.
Yeah.
So I think this is going to be a localized impact from this landslide tsunami. You have a lot of alluvial material here, so I think once you shake it, it will go.
For Herman Fritz, the low intensity of this first wave, filmed at the very moment of its birth, suggests it was triggered by a very localized phenomenon, a coastal landslide.
Here, we have evidence because we have a coastal scarp. Okay, so the scarp actually is along the shoreline. The land went into the ocean, and so we have a coastal landslide. I don't think this localized tsunami is big enough to be the main source of the tsunami that wiped away Palu or Vani on the other side of the bay.
Surveying the entire bay, researchers discover several other similar landslides, all sources of mini tsunamis. But it is by looking further inland that the full story of the Palu tsunami finally becomes clear.
Look, this is pretty amazing. Here's the rift. The tremors opened it, then closed it and opened it again.
A few hundred meters away, a second witness points out the extent of the destruction.
It collapsed all the way down there, all the way to the mosque in Ikra. All the houses collapsed at the same time, from south to north, like the slope of the house.
An immense fault line cuts through the town and then extends into the bay for tens of kilometers. Researchers finally have the answer. It is this fault that caused the Palu tsunami. After 5 days of field investigation and months of data analysis, the sequence of events is finally reconstructed. On September 28, 2018, at 6:02 p.m., a 7.2 magnitude earthquake occurs 80 kilometers north of Palu. The epicenter, correctly identified by the Jakarta Control Center, does not directly trigger the tsunami. The seismic wave travels by land at an extreme speed of 900 kilometers per hour, triggering the fault that crosses the entire bay. Within 2 minutes, landslides are provoked all along the coast, generating several mini tsunamis. The energy of all these mini tsunamis accumulates inside the bay, combining to form a powerful wave that sweeps across the town. Herman Fritz and Kostas Sinolakis' investigation has come to an end. Their reconstruction of the Bay of Palu tsunami will help improve warning systems all over the world.
We used to think that tsunamis only strike in areas where you have subduction zones. We now know, just like what happened here, that tsunamis can strike pretty much any place where you can have an earthquake. We are very concerned about this because similar earthquakes could take place in Seattle, they could take place in Southern California, they could take place in the Caribbean, and they could take place in the Mediterranean.
What walls of water, what winds, what thunder, what a horrible earthquake, what a frightening sound of the sea, and what howling of a great people.
These words by the great Italian poet Petrarch describe a strange storm over the city of Naples in the 14th century. It's an early testimony to man's fear in the face of the destructive power of nature. 700 years later, the volcanologist Mauro Rossi, who works on emergency plans for the city of Naples, was intrigued by Petrarch's description. If earthquakes and fault ruptures cause most tsunamis, volcanic eruptions can also trigger them.
Petrarch was the exceptional witness of a phenomenon that struck the city of Naples. He was sleeping, not far from the port, when he heard strange noises so powerful that he thought it was an earthquake. Petrarch ran towards the port, like the majority of the population, and saw with his own eyes the port completely devastated.
Along with the destruction, Petrarch reports hundreds of deaths and dozens of sunken ships. According to Mauro Rossi, this strange storm is clearly a tsunami.
At that time, Petrarch could not have known that it was a tsunami, since they were unknown in the Middle Ages. Now, today, we know for sure that this phenomenon was caused by a tsunami.
To determine if such a tragedy could be repeated today, the volcanologist is looking for the source of the tsunami that devastated the port of Naples in 1343. But there is no historical account of an eruption of Vesuvius, the famous volcano that dominates Naples in the 14th century. So Mauro Rossi focuses his attention on another volcano, one of the most active in the region, Stromboli. But it's located 200 kilometers from Naples. In 2002, an eruption caused the collapse of one of its walls, generating a 10-meter-high wave all around the island. The wave spread through the Tyrrhenian Sea and, although very weak, reached the Bay of Naples. Could it be that a much larger eruption on Stromboli triggered the tsunami described by Petrarch 700 years ago? On the slopes of the volcano, archaeologist Sarah Levy excavates the remains of a small collapsed church. She provides Mauro Rossi with his first clues.
We know that a dramatic event occurred due to the sudden collapse of the building, probably caused by a powerful earthquake, because large blocks of stone were found inside on the floor of the church.
In order to date the past activity of Stromboli, archaeologists examined 3 skeletons found in the remains of the church.
This skeleton was in a grave pit that was dug through the layer of collapsed tiles that fell down when the church collapsed. So this person was definitely a witness of the catastrophe, possibly a victim, possibly a survivor. This skeleton has been dated by carbon-14 in the middle decades of the 14th century.
The date of the earthquake that shook the island of Stromboli coincides with a disaster in the Bay of Naples, described by Petrarch. Yet another detail reveals the magnitude of the event.
When the church collapsed, it was not rebuilt, which is surprising and indicates a major change in human occupation at this location. It is likely that the island was abandoned until the 1600s.
This dramatic event was so violent that for more than 200 years, 10 generations, the island of Stromboli remained unoccupied. Following these revelations, Mauro Rossi starts his own excavations. He wants to find clues linking the activity of the volcano to the tsunami described by Petrarch in 1343. At a depth of more than 4 meters, the volcanologist finally uncovers a fabulous deposit.
This tsunami deposit is by far the largest we've ever found, and we've dated it to 1350, as evidenced by the materials in it. Look at the size of these perfectly round rocks. They must have come from the beach. The presence of such consistent elements proves that the tsunami was driven by an extraordinary force.
All the facts coincide. The powerful wave that projected these rocks 200 meters from the beach occurred at precisely the same time as the earthquake that destroyed the small church on the island. For Mauro Rossi, there is a clear link between the eruption of the volcano and the tsunami. La Sciara del Fuoco. It is on this impressive slope that all the volcanic material ejected by Stromboli accumulates. 700 years ago, following an eruption, the volcanologist believes that the Sciara del Fuoco suddenly shed its millions of tons of accumulated debris, causing a tsunami that spread to the Bay of Naples.
Given the current activity of Stromboli, it's assumed that the level of detritus on the Sciara del Fuoco would be comparable to that of the Sciara at the time Petrarch describes the tsunami.
For Mara Rosi, the landslide caused by the 2019 eruption is a harbinger of a much more serious disaster to come. The Sciara del Fuoco could collapse into the sea at any moment. The island of Stromboli is monitored 24 hours a day to alert the authorities, inhabitants, and tourists. But what about Naples? What would be the consequences of a tsunami hitting a city of 1 million inhabitants?
The population is completely unaware that a tsunami from Stromboli could hit Naples. In the case of infrequent natural phenomenon, people tend to believe that there is no imminent danger.
Researchers at the University of Bologna have made a model of the path of the 1343 tsunami. It gives an idea of what could happen today.
It would take barely 30 minutes for the tsunami to leave Stromboli and hit the Gulf of Naples. And here, the consequences would be unbelievable. All the boats in the harbor behind me would be thrown into the streets. The water would rush into the subway and drown its occupants. The streets full of people would be submerged. It would really be an apocalyptic scenario if we weren't able to sound the alarm.
Earthquakes, fault slides, volcanic eruptions. All sorts of tectonic activity can trigger tsunamis. Research carried out over the last 15 years has made it possible to perfect warning systems and better adapt them to each risk zone. In Japan, a country at the forefront of tsunami science, the technology is the most advanced. Here, researchers know exactly where the next disaster will come from. These images are not those of a disaster movie, but a public service announcement from the Japanese authorities. Broadcast in March of 2018, it's intended to prepare the population for a tsunami that scientists give an 80% chance of occurring in the next 30 years. The film explains how to react and behave, but also predicts the likely scale of the disaster. 350,000 victims and widespread damage that would affect the Japanese economy for at least 20 years. The cause? The rupture of the Nankai Fault that runs along the west coast of the country for 900 kilometers.
The threat of the Nankai Trough is very specific because it is located in front of all the economic centers of Japan. Whether Tokyo, Osaka, or Nagoya, all these cities are in vulnerable areas.
No technology can predict an earthquake. But the Japanese have set up an extensive monitoring system to immediately warn the population.
It's a matter of listening to the fault, knowing when it will move, and being able to sound the alarm as quickly as possible. And for that, we have the Donet system, which is just outside Osaka Bay.
The Donet system is the most sophisticated seismic detector in the world. 29 underwater mini observatories. Pressure sensors, seismometers, accelerometers are installed directly on the fault line off the coast of Osaka to give the alert as soon as the first tremors occur.
The tsunami would arrive between 3 and 5 minutes in the first cities with waves of 20 to 30 meters. Then the wave enters Osaka Bay and floods parts of Osaka, parts of Kobe, and especially all the islands that have been artificially created. Depending on the scenarios, we expect waves of 3 to 5 meters and that would take between 30 and 45 minutes.
In order to establish the most effective evacuation plans and test protective walls, the Disaster Prevention Center at Kyoto University simulates the effects of a Nankai Fault tsunami in a pool.
We're almost certain that it will be an earthquake of at least magnitude 9.0, and that it will cause a tsunami.
Professor Hireshi recreates the arrival of a wave with an average height of 20 meters, the equivalent of a 6-story building, on a city directly facing the Nankai Fault. In spite of seawalls built to reduce the energy of the waves, coastal buildings would quickly be submerged under several meters of water. These pool simulations are supplemented by virtual simulations. One developed by Professor Hireshi's team allows us to anticipate the progression of a tsunami in Tokyo Bay. Although it is 5 kilometers from the sea, the area around the Olympic Stadium could be hit by a 9-meter-high wave.
Simulations are carried out to determine hazardous locations. For example, a road will be hit by a wave very fast, so you should not take refuge there. This building will have its entrance blocked by the current of the tsunami, so you should not go there.
These models enable Kyoto University to create an interactive evacuation plan. In the event of an alert, a mobile phone application shows the progression of the waves and designates the nearest protected areas.
We've got messages coming in on our cell phones, on the internet. When you watch TV, you have messages coming to you too, and they tell you where you have to run to be safe.
Fleeing and finding refuge is essential, but limiting the impact of destruction is just as important. As the 2011 tsunami demonstrated, port areas are among the most dangerous sites. Ships can become giant projectiles. For Professor Hashimoto of the University of Kobe, evacuating them quickly in the event of an alert is a priority.
Osaka Bay is very lively. Every day and at any given moment, there are 30 to 50 boats sailing there. We have no guarantee that in the event of a tsunami, a situation that may have never experienced, everyone would keep their cool and that the ships would evacuate one after the other in an orderly fashion. That is why we're developing an artificial intelligence system which will enable ships to evacuate or maneuver automatically.
Despite technological advances, Japan is living on borrowed time. Like Osaka, a megalopolis of 8 million inhabitants and the country's second largest economic center. A city built over time on embankments, below sea level, surrounded by hundreds of kilometers of protective walls.
What happened in 2011 was that the earthquake had weakened all the structures. Part of the walls had fallen with the quake. So when the tsunami came, what we thought was effective was no longer effective.
To date, even the most sophisticated technologies cannot predict earthquakes. These artificial islands reclaimed from the sea, built with houses, shopping centers, and petrochemical industries, could be destroyed in an instant. Faced with coming disaster, only education and informed reactions of the population will make it possible to save lives. We think we're taming nature, but nature dominates us. Around the world, the science of tsunamis is making great strides, but each new disaster challenges the progress that has been made to better protect us.
If we build power plants, hospitals, public buildings, houses in areas that there is a high hazard, we are adding layers and layers of vulnerability. And with time, what we're finding around the world is that our vulnerability from disasters keeps increasing instead of diminishing.
The shoreline has always attracted humankind, but its rapid urbanization creates more and more danger. While ever more sophisticated technologies allow us to be alerted as soon as possible, learning to read nature with common sense remains more vital than ever.
We say this worldwide. If you're near the coast and you feel any kind of ground shaking that lasts more than 15 seconds, move away from the beach.